Hybridization of atomic orbitals, the sp3, sp2, and sp models. The atomic structures from the periodic table of atoms such as carbon, nitrogen, and oxygen do not adequately explain how these atoms use orbitals to form bonds in molecules. A hybridization model has therefore been developed to explain real structures, for example, how all the bond lengths and angles are equivalent in methane. So why do we need this idea? If we look at the structure of water, we find that both O to H bonds are equivalent and both lone pairs are equivalent. This isn't possible by using the electron configuration of oxygen from the periodic table. If we look at what goes into making the water molecule, each hydrogen brings with it a single 1s electron. Oxygen has 8 electrons in the configuration 1s2, 2s2, 2px2, 2py1, and 2pz1. The two paired up sets of electrons at the 2s and 2p levels, which could be the lone pairs, are not equivalent. To make the hybrid orbital idea easier to visualize, we can convert the ground state electronic structure of oxygen into an energy diagram, which presents the orbitals and their electrons as increasing in energy as they get further from the nucleus. It should now be easier to appreciate that the two sets of paired electrons are not the same, so we need to modify the picture to match what occurs in water. In a sense, we can work backwards since we know we need 4 equivalent orbitals, 2 of which will contain lone pairs, and 2 that will contain single electrons capable of bonding with hydrogen atoms. The sp3 designation simply comes from the orbitals that were mixed, i.e. a single s and 3 p orbitals. The 1s is left alone and not changed. Since the sp3 orbitals are equivalent, they will adopt a tetrahedral pattern in space, so that each orbital is as far away as possible from the others. The shape of each individual sp3 orbital reflects its mixture of s and p characteristics. Once we populate the sp3 atomic orbitals, filling up singly before we double up, the 2 equivalent lone pairs and 2 equivalent singly occupied orbitals become apparent. At this point, we need to remember that these are atomic orbitals, and we have not yet overlapped anything to make bonds and molecular orbitals. As we look to expand the hybridization idea, keep in mind that there are only 3 patterns we need to know for the organic sequence, namely sp3, sp2, and sp. These will differ by the number of p orbitals that are mixed. In general, if no pi bonds are present, then the sp3 pattern is used, with carbon, nitrogen, and oxygen only differing by the number of electrons involved. Notice that the lone pair in N and the 2 equivalent lone pairs on O are now taken care of, and spare single electrons are left over for making sigma bonds to other atoms. The sp3 model for carbon displays its atomic orbitals into a tetrahedral shape in 3-dimensional space. This will account for the geometry of methane, in which all bond lengths and bond angles are the same. Each of the molecules here contain only single bonds to C, N, or O, and therefore only the sp3 pattern is needed for each of those atoms. Since pi bonds are made from overlapping p orbitals, we need a different hybridization pattern for the atoms involved. When we are mixing atomic orbitals here, we need to leave a p orbital alone and only mix enough orbitals to match the required number of sigma bonds and lone pairs. Notice that hybrid orbitals are always used to house lone pairs and to make sigma bonds to other atoms. The trigonal planar geometry of the sp2 hybrid atom is shown here. The 3 hybrid orbitals adopt a flat shape with angles of 120 degrees between each to minimize their interaction. The leftover p orbital must then be orthogonal, or at 90 degrees, to the hybrids. In these examples, each C, N, and O atom that is involved in a pi bond will be sp2 hybridized. C has formed 3 sigma bonds from hybrid orbitals and 1 pi from the unhybridized p orbital. N has 2 sigma bonds from hybrids, 1 lone pair housed in an sp2 orbital, and 1 pi bond from p. O has 1 sigma bond from an sp2 orbital, 2 lone pairs in hybrid orbitals, and 1 pi bond from the leftover p orbital. The third hybrid pattern required, sp, is needed when an atom is involved in 2 pi bonds. Here the hybrids again go to sigma bonds and lone pairs, while unhybridized p orbitals go to pi bonds. Notice that the hybrid orbitals dictate the linear geometry around C and N in each case, while O rarely participates. In these examples, the non-hydrogen atoms are in either of the 3 hybrid patterns. In the first molecule, the highlighted functional groups both contain linear sp hybridized atoms. In the second, the left-hand function has an sp hybrid C, while the right-hand group has sp2c and O atoms. The third example has a central sp hybrid C atom. Notice that the carbons in the alkyne on the left and the diamide on the right are both sp hybridized since they are both involved in 2 pi bonds. Which atom and hybridization pattern does this arrangement match? The electronic configuration matches nitrogen, and the 3 hybrid orbitals and single p orbital match the sp2 pattern. Which atom and which of the three hybridization patterns is represented here? The 4 valence electrons matches carbon, while the 2 leftover p orbitals are part of an sp hybridized atom. To test your understanding here, match the electron pattern to the atom and hybridization model. No leftover p orbitals means this is the sp3 pattern, while the 2 lone pairs mean the atom is oxygen. Indicate which atom in this molecule has sp hybridization. The carbon with 2 pi bonds is the only one that matches the requirement for sp. Find the only sp3 atom in this compound. The central carbon is the only sp3 atom present. All of the others are sp2 hybrids. Which atom or atoms in this molecule are sp2 hybrids? The carbonyl group contains sp2 hybridized C and O atoms. With these 3 hybridization patterns on board, sp3, sp2, and sp, you should now be able to predict which are present in any organic molecule and what the local geometries will be around those atoms.